There is a thought experiment that physicists and philosophers have been running for 75 years, and the more carefully you run it, the more it starts to feel less like intellectual curiosity and more like something you'd prefer not to have encountered. It starts simply. The universe is 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. A substantial fraction of those stars have planets. A substantial fraction of those planets are in the right temperature range for liquid water. The raw materials for chemistry, for biology, for life, carbon, hydrogen, oxygen, nitrogen, phosphorus, are not rare. They're among the most common atoms in the cosmos. They seed molecular clouds, they float in the spaces between stars, they were present in the galaxy billions of years before our solar system formed. Given all of this, given the sheer scale of the universe and the abundance of the ingredients, the expectation is clear. The galaxy should be full of life, full of intelligence, full of civilizations at various stages of development, some in their infancy, some ancient beyond reckoning, some already spread across star systems, some that have been broadcasting their presence across electromagnetic frequencies for millions of years before the first multicellular organism appeared on Earth. And yet, silence. We have been listening for signals since Frank Drake pointed a radio telescope at a nearby star in 1960. We have catalogued thousands of exoplanets, including hundreds in habitable zones. We have sent probes to the edge of the solar system. We have scanned the sky in radio, in optical, in infrared, looking for the waste heat of alien megastructures, for the chemical signatures of industrial civilizations, for anything that would confirm what the math says should be obvious, that we are not alone, nothing. This is the Fermi Paradox, named for Enrico Fermi, who encapsulated it at a lunch table in 1950 with 4 words: "Where is everybody?" And in 75 years of serious scientific effort, nobody has found a satisfying answer. But here is what most people don't know. Most people who have heard of the Fermi Paradox think of it as an open mystery, a puzzle that will eventually be resolved when we develop better instruments, search more of the sky, listen in more frequency bands. A mystery of the where. Where are they? Hiding behind what rock? Broadcasting on what frequency we haven't tried yet? What a growing number of physicists, astrobiologists, and philosophers of science now believe is that the Fermi Paradox is not primarily a mystery of where, it is a mystery of when. And the most precise, most carefully argued, most evidence-consistent solution to the paradox is not that aliens are hiding, or that we haven't looked hard enough, or that the universe is somehow less hospitable than it appears. The solution, the one that fits the data, that fits the timescales, that fits the specific developmental stage at which we find ourselves, is the one that most people who encounter it wish they hadn't, because it isn't about them, it's about us. The solution to the Fermi Paradox that best fits everything we know is that there is a barrier, a filter, in the developmental pathway from chemistry to civilization. A step that virtually no species survives. A wall that intelligent life reliably hits, at a specific stage, and that almost nothing gets past. And the terrifying part, the part that should keep you awake if you think about it carefully enough, is not that this filter might exist. It is that the evidence increasingly suggests the filter is not behind us, it is ahead. Now, I want to be precise about what the evidence increasingly suggests actually means, because this topic is prone to overclaiming in both directions. There are people who read the Fermi Paradox and conclude too hastily that because the galaxy is silent, something is definitely going to kill us soon. And there are people who read it and conclude, also too hastily, that the silence is easily explained by our current detection limitations, and we shouldn't be worried. Neither of these is the position I'm going to defend. What I'm going to defend is more specific and more uncomfortable than either of those. I'm going to show you that several distinct lines of evidence, from recent astronomy, from astrobiology, from probability, theory, from the specific nature of the technologies humanity has developed, converge on the same conclusion. Not with certainty, not with the kind of proof that closes the question, but with a preponderance of evidence that a careful, honest analyst should take very seriously. The kind of preponderance that, in other domains of risk assessment, would generate urgent policy responses. I want you to hold 2 things in mind simultaneously throughout this video. First, we genuinely don't know the answer to the Fermi Paradox. The filter could be behind us. we might be rare and lucky and the road ahead genuinely open. Second, the most specific, most recent, most carefully quantified analysis of the available evidence does not favour that comfortable reading. And the discomfort of the alternative is not a reason to avoid it. This video is about that evidence, not the abstract philosophical version of it, the specific empirical, recent discovery version of it. The papers published in the last 5 years that have quietly, methodically narrowed down the location of the Great Filter in ways that previous analysis couldn't. The astronomical observations that have begun to tell us what we should expect to find if the filter is ahead. The specific markers, the specific signatures of civilizational death that we are, for the first time in history, developing the tools to look for. And it is about what it means to live at this specific moment in history, at the precise developmental stage where the evidence says civilizations are most likely to fail. With the specific technologies that the evidence says are most likely to do the killing, let's go through this carefully, because the implications don't land unless the argument is built properly, and built properly, they land very hard. Chapter 1. The silence is not what you think. The first thing to establish is that the Fermi Paradox is a much stronger argument than most people realise. The popular presentation of it, "Why haven't we found aliens yet? Isn't the universe big?" understates the problem by a wide margin. The actual quantitative structure of the paradox is more severe, and understanding how severe it is sets the context for why any proposed solution needs to be correspondingly extreme. Here is the core of the argument, built from the ground up. The Milky Way galaxy is approximately 13.6 billion years old. The first stars formed within the first few 100 million years, but those early stars were composed almost exclusively of hydrogen and helium. The heavy elements required for rocky planets and carbon-based chemistry hadn't been forged yet. It took several generations of stellar birth and death to seed the galaxy with sufficient concentrations of carbon, oxygen, iron, and the other heavy elements that planetary chemistry requires. By about 9 to 10 billion years ago, the metallicity of the galaxy in regions like ours had reached levels sufficient for Earth-like rocky planets and carbon-rich chemistry to form and persist. This means the window for civilizations like ours, chemistry-based life on rocky planets, has been open for roughly 9 to 10 billion years. In that window, there are somewhere between 20 and 40 billion potentially habitable planets in the Milky Way, depending on how conservatively you define potentially habitable. Even if you restrict to sun-like stars and apply every conservative correction factor you can find, the number of candidate planets is in the billions. Now, what does it mean for a civilization to be capable of galaxy-scale influence? Not necessarily physical colonization. We're talking about any influence detectable from interstellar distances, radio leakage, atmospheric biosignatures, Dyson structures around stars for energy capture, megascale engineering visible in infrared, or, simplest of all, deliberate electromagnetic broadcasts. Any technological civilization operating at or beyond our current level for more than a few hundred years would produce some of these signatures. The question is, how long does interstellar influence take to propagate? Radio signals travel at the speed of light. The Milky Way is 100,000 light-years across. A civilization broadcasting from the other side of the galaxy started broadcasting 100,000 years ago for their signal to reach us now. But in a galaxy 10 billion years old, 100,000 years is 0.001% of the available time. Civilizations broadcasting for any significant fraction of the galaxy's history would have had signals crossing the full galactic diameter millions of times over. Physical colonization doesn't require faster-than-light travel to fill the galaxy on cosmological timescales. A civilization that expands at 1% of the speed of light, 3,000 kilometers per second, roughly the speed of the fastest chemical rockets we can imagine, would traverse the full diameter of the galaxy in 10 million years. In a 10 billion year window, such a civilization could have colonized the galaxy 1,000 times over. Even at 1/10,000th of the speed of light, a leisurely pace by any conceivable interstellar standard, full galactic colonization happens within the available window, but it doesn't even require continuous active colonization. Von Neumann probes, self-replicating spacecraft that harvest resources from each star system they visit to build copies of themselves and send those copies onward, would expand at exponential rates limited only by the travel time between stars. Even without faster-than-light travel, a civilization launching a single self-replicating probe could, within a few million years, have descendants of that probe in every star system in the galaxy. The mathematics of exponential growth operating over millions of years is so overwhelming that the absence of such probes in our solar system, no artifact, no automated factory, no ancient machine quietly dismantling asteroids in the outer belt, is one of the most striking negative results in the history of the Fermi Paradox. We have at this point surveyed the solar system with enough thoroughness to say with reasonable confidence that no obvious alien megastructure or automated probe or resource extraction operation is present. The asteroid belt has been catalogued extensively. The outer solar system is being mapped by increasingly sensitive surveys. No technological artifact has been found. The solar system appears to be in exactly the condition you'd expect from purely natural processes operating over 4.5 billion years with no external technological interference. This negative result is often underappreciated. The solar system is not just the nearest star system to wherever any hypothetical alien civilization might have originated. It is a star system that has existed for 4.5 billion years, in a galaxy 9 to 10 billion years into its habitable phase, with every reason to have been visited or colonized, or at minimum probed by any of the billions of potentially technological civilizations that could have existed before us. The absence of any trace of their presence is powerful evidence that either they don't exist or they fail to reach the stage of interstellar capability. The conclusion is unavoidable. If even one technological civilization emerged in the Milky Way more than about 10 to 50 million years before us, and the available window is 9 to 10 billion years, so one civilization 10 million years ahead of us would be at the 99.9% point of the window, meaning 99.9% of civilizations would be older. That civilization would have had more than sufficient time to make its presence known across the entire galaxy. Not subtly, not in a way requiring instruments more sensitive than we currently have, clearly, unmistakably in every direction, and we see nothing, hear nothing, find nothing. The silence is not the silence of a universe that hasn't been asked the question loud enough. It is the silence of a universe that either has no one to answer, or in which everyone who could answer has stopped answering, or in which something prevents civilizations from reaching the stage where they would answer. A subtler version of the same argument makes it even more acute. The universe itself has been enriched over time, more heavy elements, more complex chemistry, more potential for life with each passing generation of stars, which means that if life is common, it should be increasingly common over cosmic time. The civilizations that emerged 5 billion years ago, or 8 billion years ago, should still be present in some form. Their physical structures, their engineered artifacts, their electromagnetic signatures should still be traversing the galaxy. Galaxies that host ancient civilizations should look different from those that don't, and we should be able to see the difference. We don't. Every galaxy we examine looks consistent with purely natural processes. Every star system we measure appears unmodified by intelligence. Every spectral analysis of every exoplanet atmosphere we've been able to perform shows chemistry consistent with natural geological and biological processes, nothing that clearly requires industrial civilization. The silence is total, not partial, not we've only searched a fraction of the sky. Total in the sense that the universe-scale signatures of advanced civilizations, signatures that should persist for millions or billions of years, are absent from everywhere we look. This is what requires explanation. This is why proposed solutions to the Fermi Paradox need to be powerful enough to account for complete, systematic, universe-scale silence over 10 billion year timescales. Weak solutions, they haven't gotten around to broadcasting yet. They're using communication methods we haven't thought of. They prefer to stay on their home planets, are insufficient because they don't account for the sheer timescales involved. Given 10 billion years, an expanding civilization doesn't need luck or motivation, or a specific communication philosophy. Physics alone produces detectable signatures. The solution to work must prevent essentially every technological civilization from becoming the kind of civilization that leaves 10 billion year detectable signatures. It must prevent it reliably, universally, across all chemistries, all planetary types, all physical environments, all evolutionary trajectories. It must prevent it at a rate approaching 100%. Something is killing them, or something is preventing them from reaching the stage where they could leave such signatures and whatever it is extraordinarily effective. Chapter 2: The Great Filter, Placing the Wall. In 1998, economist Robin Hanson published a short but devastating paper titled The Great Filter, or Are We Almost Past It? In it, he formalized the Fermi Paradox as a filtering problem. If the expected number of galaxy-colonizing civilizations is large, and the observed number is 0, then somewhere in the chain of steps from simple chemistry to galaxy-colonizing civilization, there must be a step, or a series of steps, whose combined probability is small enough to bring the expected number close to 0. He called this the Great Filter, and he asked the question that matters most: where is it? The chain of steps from chemistry to civilization looks something like this, in rough sequence. First, the right physical environment, a star in the right part of the galaxy, stable for billions of years, with a habitable planet in the right orbital range. Second, the origin of life from non-living chemistry, abiogenesis. Third, the development of cells with nuclei and complex internal machinery, eukaryotic life. Fourth, multicellular organisms. Fifth, sexually reproducing complex animals. Sixth, intelligent social animals capable of cumulative culture. Seventh, technological civilization capable of interstellar communication or colonization. Each step requires the previous steps. Each step has some probability of occurring, given the previous steps. The product of all those probabilities gives the overall probability of a galaxy-colonizing civilization per habitable planet. If this product is small enough, if even one step in the chain has a probability of, say, 1 in a billion per habitable planet per billion years, then the expected number of galaxy colonizers is close to 0, and the Fermi silence is explained. The filter doesn't have to be a single catastrophically improbable step. It can be a combination of several moderately improbable steps that together produce the required overall rarity. What matters is that somewhere in the chain, the combined probability is very small. Now here is the crucial point that Hanson's paper made, and that has become more important with every subsequent discovery in astrobiology and exoplanet science. If the Great Filter is in our past, if the hard step or steps that make galaxy colonizers rare are ones we have already passed, then the silence is explained by our own rarity. We are the rare exception. We got through the hard part. The galaxy is quiet because life, or intelligence, or civilization rarely emerges, and we got lucky. In this scenario, the road ahead is open. We are not typical, we are unusual, and our unusual existence, our position past the hard step, means we have a reasonable probability of becoming exactly the kind of galaxy-colonizing civilization that would make the Fermi Paradox worse for anyone asking the question from an adjacent star system. If the Great Filter is in our future, if the hard step is one we have not yet reached, then the situation is fundamentally different and fundamentally worse. It means that civilizations like ours, chemical rocket capable, nuclear weapon possessing, industrialized, globally communicating civilizations at our specific technological level, routinely fail to reach the galaxy colonizing stage. Something happens to them, reliably, before they make the transition. We are not unusual in being where we are typical, and the filter that takes out the typical cases is ahead. This is the structure of the argument, and the question of which scenario is correct, filter behind or filter ahead, is not merely a philosophical question. It has become, in the last 15 years, an empirical question, one that can be addressed with increasing precision using actual data. Let's look at what the data says. The most important recent development in Fermi Paradox research is the application of Bayesian reasoning to the uncertainty in the Drake equation parameters. The Drake equation is a framework for estimating the number of currently communicating technological civilizations in the galaxy. It multiplies together several factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction where life emerges, the fraction where intelligence emerges, the fraction that develop technology, and the average lifespan of technological civilizations. For years, the practice was to plug in optimistic estimates for the uncertain parameters, estimates informed by the rapid emergence of life on Earth, the ubiquity of potentially habitable planets found by Kepler, the general friendliness of the universe's chemistry to life. These optimistic estimates produced large numbers of expected civilizations, millions in Carl Sagan's famous estimate, making the Fermi silence deeply paradoxical. In 2018, a team from Oxford's Future of Humanity Institute, Anders Sandberg, Eric Drexler and Toby Ord, published a paper doing something that should have been done decades earlier. Instead of using point estimates for the uncertain parameters, they used probability distributions that honestly represented the full range of scientific uncertainty. They drew on the actual peer-reviewed literature for each parameter, constructed log-uniform distributions covering the plausible range for each factor, and propagated those distributions through the Drake equation. The result was striking. When the uncertainty is properly accounted for, when you don't paper over the genuine scientific ignorance with false precision, the probability distribution for the number of communicating civilizations in the galaxy has a substantial mass near zero, including a probability of 21 to 32% that we are alone in the observable universe, including a probability of 38 to 53% that we are alone in the Milky Way. This doesn't mean we are alone. It means our uncertainty is large enough that being alone is genuinely plausible, consistent with current evidence, not a fringe hypothesis. The Fermi silence in this analysis is not strongly paradoxical. It is what you'd expect if the actual parameters are in the less optimistic end of their plausible ranges. But here is the implication that the Oxford paper doesn't emphasize, but that follows directly from the analysis. If the reason we might be alone, if the reason the Drake equation product is close to zero, is that the emergence of life from chemistry is extremely rare, then the filter is at the abiogenesis step. Behind us, we got past it. The road ahead is open. If the reason the product is close to zero is that the emergence of complex, intelligent, technological life from simple life is extremely rare, if the hard step is the one that happened in the last 600 million years rather than the first 3 billion, then the filter is also behind us, at a later step but still behind. But if the reason the product is close to zero is that technological civilizations have short lifespans, if the L factor in the Drake equation, the average communicating lifespan of a civilization, is a few hundred years rather than millions, then the filter is ahead. Civilizations emerge, develop, technology, and then fail rapidly and reliably before they can expand or broadcast for long. The Bayesian analysis cannot tell us which of these is the case, but it can tell us which factor is doing the most work in producing near-zero expected civilizations, and it turns out that the L factor, the lifespan factor, has a disproportionate impact. Small values of L devastate the expected number of civilizations far more severely than small values of the biological factors, because L determines whether the civilizations that do emerge leave any lasting signature, or whether they flash briefly and go dark. Here is a concrete illustration of why L matters so much more than the other factors. Suppose the probability of life emerging on a habitable planet is 1 in a million, a very low probability that would make life quite rare. With roughly 20 billion potentially habitable planets in the Milky Way, this still produces 20,000 life-bearing worlds in our galaxy. Suppose further that the probability of intelligence emerging from life is 1 in 1,000. That gives 20 technological civilizations in the galaxy's history. Not 20 right now, 20 total, over the galaxy's 10 billion year habitable lifetime. That's sparse, but not zero. Now, how long does each of those 20 civilizations last as a detectable, communicating civilization? If L is 1 million years, if each technological civilization survives for 1 million years once it develops technology, then at any given time, there should be roughly 20 times, 1 million divided by 10 billion, civilizations simultaneously active, which is about 0.002, well below 1, making simultaneous coexistence unlikely. But each civilization's 1 million year broadcast window produces a detectable signature that propagates across the galaxy, potentially surviving long after the civilization itself ends. Radio signatures from a civilization that flourished and died 500 million years ago would still be traversing the galaxy. But if L is 200 years, if technological civilizations typically exist for only 200 years before failing, the picture is completely different. Each civilization's detectability window is 200 years. In 10 billion years of galactic history, 20 civilizations times 200 years each equals 4,000 years of total broadcast time, scattered across 10 billion years. The probability of one of those brief broadcast windows coinciding with our ability to detect it from our location is vanishingly small. The galaxy is effectively silent, not because civilizations are rare, but because they are brief. And this is the key insight for the filter ahead argument. You don't need life to be rare. You don't even need intelligence to be rare. You only need technological civilizations to be short-lived. If the thing that kills civilizations reliably is the technology itself, if the development of nuclear weapons, engineered biology, and artificial intelligence is sufficient to destroy most civilizations within a few centuries of their development, then the galaxy would look exactly the way it looks, empty of detectable signals, silent. Not because we are alone, but because everyone who gets to our stage ends quickly. Chapter 3. The evidence that points forward. Let's get specific. What actual evidence from the last 10 to 15 years of scientific research bears on the question of whether the Great Filter is mostly behind us or mostly ahead? There are 3 categories of evidence. The first comes from astrobiology and the search for life in our own solar system. The second comes from exoplanet atmospheric spectroscopy. The third comes from the specific timing argument, the observation that we appear to have arrived at the Fermi question at a very specific and very suspicious moment in our own technological development. The solar system evidence. The most important single finding bearing on the location of the Great Filter is the distribution of potentially habitable environments in our own solar system. When Viking landed on Mars in 1976, the expectation was that Mars might be a close second to Earth in habitability, a cold, dry desert, but still potentially hospitable to microbial life. Viking's biology experiments produced ambiguous results that have been debated ever since, but the general conclusion was that Mars's surface is, at present, hostile to life. What has changed dramatically since Viking is the picture of Mars's ancient past and the picture of the outer solar system? Mars, we now know, had liquid water flowing on its surface for hundreds of millions to possibly 1 billion years in the early solar system. NASA's Perseverance rover has confirmed the presence of ancient lake sediments in Jezero crater, ancient riverbeds, ancient deltic deposits, a geological record of a wet, potentially habitable world that existed 3 to 4 billion years ago. The organic molecules found by Perseverance in those sediments are not proof of life, but they are the chemistry of life's potential, preserved in rock for billions of years. Europa, the moon of Jupiter, has a liquid water ocean beneath its icy crust that contains more liquid water than all of Earth's oceans combined, heated by tidal interactions with Jupiter, potentially in contact with a rocky seafloor that could provide the chemistry for hydrothermal vents. Enceladus, the moon of Saturn, is actively venting water vapor and organic molecules into space from fissures in its icy south pole. Direct evidence of a subsurface ocean in contact with a rocky core, with complex chemistry including hydrogen gas, and complex organic molecules that on Earth are associated with the chemistry surrounding deep-sea hydrothermal vents. Titan has a global cycle of liquid hydrocarbons, lakes and rivers and rain, not of water, but of methane and ethane, with complex organic chemistry that Carl Sagan speculated could support a different kind of life. The point is this: our solar system contains multiple potentially habitable environments, not Earth alone. At minimum, Mars's ancient past, Europa's present, Enceladus's present, and the count goes up if you include Titan and the recent discoveries about Venus's lower atmosphere. This richness of potentially habitable environments in a single solar system is critical for the filter location argument in the following way. If life is rare, if the origin of life from chemistry is the Great Filter, a catastrophically improbable event that happens only once per many billions of habitable planetary environments, then we should expect most planetary systems to be lifeless. We should expect Mars to be lifeless, past and present. We should expect Europa's ocean to be a sterile cold sea. We should expect Enceladus to be venting complex organic chemistry, but no biology. If, instead, life is common, if the origin of life is not the filter, if abiogenesis occurs readily wherever chemistry and liquid water and energy sources combine in the right way for long enough, then we should expect Mars to have harboured life in its wet past. We should expect Europa's ocean to contain life. We should expect Enceladus's vents to host microbial communities. We should expect life to have arisen independently multiple times in our solar system alone. This matters because finding life in our solar system, even extinct life, even fossilized microbial traces in Martian rocks, would dramatically shift the probability estimate for where the filter is. If life arose independently on Mars, that means life arises readily wherever conditions permit, which means the filter is not at abiogenesis, which means the filter is somewhere further along the chain, somewhere in the path from simple microbial life to complex animals to intelligence to technology to long-lived civilization. And here is where the logic becomes genuinely terrifying. Because if life is common but the galaxy is silent, if simple microbial life arises readily but the galaxy still shows no signs of technological civilization, then the filter that produces the silence must be between simple life and long-lived technological civilization, which means it must be in the path that we are still traveling. The filter that destroys civilizations is something that happened to civilizations that had already produced life, had already produced complex animals, had already produced intelligence, had already developed technology. It is something that happens at or near the technological stage. That is us. We are approaching the filter from behind. And what lies in the path between where we are and a stable, multi-planetary, interstellar civilization is, in this analysis, a wall that almost no one gets through. The exoplanet evidence. The James Webb Space Telescope began science operations in 2022, and its first atmospheric characterizations of exoplanet atmospheres have already changed the conversation. JWST can detect molecular absorption features in the atmospheres of planets transiting their host stars. It can identify water vapor, carbon dioxide, methane, ammonia, and, in principle, molecules associated with biological activity like oxygen, in combination with methane or dimethyl sulfide. In 2023, JWST published a tentative detection of dimethyl sulfide in the atmosphere of K2-18b, a sub-Neptune world in the habitable zone of a red dwarf star 120 light-years away. Dimethyl sulfide on Earth is produced almost exclusively by marine phytoplankton. It is a biosignature, a molecule whose presence in a planetary atmosphere at detectable concentrations is very difficult to explain without biology. The detection was tentative. The signal was at a 3 sigma confidence level, below the 5 sigma threshold for a formal detection claim, and has not yet been confirmed with additional observations. But the significance is not whether K2-18b specifically harbours life. The significance is that JWST can detect biosignature candidates in the atmospheres of planets 120 light-years away. We now have an instrument capable of looking for life on other worlds in something approaching a systematic way. Over the next decade, as JWST accumulates more observation time, and as next-generation telescopes like the extremely large telescope come online, the catalogue of characterized exoplanet atmospheres will grow from dozens to hundreds to potentially thousands. We will have, for the first time, actual data about the frequency of life-indicating chemistry in the atmospheres of other worlds. Now here is the implication for the filter location argument. If JWST finds biosignatures in the atmospheres of a significant fraction of habitable exoplanets, if oxygen-methane combinations or dimethyl sulfide detections become common over the course of the 2020s and 2030s, this is the worst possible news from a great filter perspective. It means life is common. It means the filter is not at abiogenesis. It means the filter that produces the Fermi silence is somewhere between has biology and has long-lived technological civilization. It means the filter is close to us. If JWST finds that biosignatures are rare or absent, if hundreds of characterized habitable zone exoplanet atmospheres show nothing but abiotic chemistry, this would be some evidence, though not conclusive evidence given JWST's sensitivity limits, that the filter might be at or near biogenesis, that life itself is rare, that we got lucky at the very first step. This would be, relatively speaking, the good news scenario. The hard step is behind us, and whatever is ahead is not a near-universal civilization killer. The discovery we make over the next 10 to 20 years with JWST and its successors will be one of the most important pieces of evidence ever collected about the location of the Great Filter. The scientific community knows this. What is less widely appreciated is that the good discovery, no biosignatures, life is rare, is probably the less likely outcome, given what we already know about chemistry's friendliness to biology and the abundance of potentially habitable environments. The most probable discovery, given the current state of evidence, is biosignatures on some fraction of habitable worlds, which is also the discovery that most directly points the finger at the filter being ahead. The timing argument. This is the one that should sit with you the longest. It is also the one that receives the least coverage in popular treatments of the Fermi Paradox, possibly because its implications are the most personal. Consider what technological civilizations look like as they pass through the critical developmental phase. Before industrialization, a civilization's observable footprint, its electromagnetic signatures, its atmospheric chemistry, its use of planetary resources, is essentially indistinguishable from a world with only natural biological processes. A medieval civilization on Earth would look, to an observer with JWST-class telescopes, like a world with anomalous biology, but nothing that clearly screams technology. Pre-industrial civilizations are, in a real sense, below the detection threshold of the tools we are developing to search for civilizations. After a civilization achieves radio communication capability, its electromagnetic footprint becomes potentially detectable. Radio leakage from a civilization broadcasting at Earth's current levels is marginal at interstellar distances, with current instruments, but detectable in principle, and certainly detectable with more advanced receivers at closer ranges. After a civilization achieves industrial-scale energy use, its atmospheric chemistry begins to diverge from purely natural processes. The industrial production of fluorinated gases, the burning of fossil fuels producing CO2 anomalies, the emission of exotic compounds that have no natural sources. After a civilization begins large-scale space colonization, its star system footprint becomes more obvious. Megastructures, altered planetary orbits, waste heat signatures. In between pre-industrial invisibility and post-expansion unmistakability, there is a narrow window. A window measured in centuries, perhaps millennia. A window in which a civilization has developed technology powerful enough to significantly alter its environment, powerful enough to create existential-scale risks. Nuclear weapons, engineered pathogens, runaway climate change, misaligned artificial intelligence, but not yet stable and distributed enough to survive the failure of any one of those risks. We are in that window right now. Let's be precise about when the window opened. On July 16th, 1945, the first nuclear weapon was detonated at the Trinity test site in New Mexico. In a single morning, humanity crossed a threshold that no other species in Earth's history had ever crossed. The threshold of possessing technology capable of civilizational-scale self-destruction. Before that morning, the worst catastrophes in human history, plague, war, famine, climate change, were things that could kill large fractions of human populations, but could not, in principle, end civilization itself or render the planet permanently uninhabitable. After Trinity, that calculus changed. In the years since 1945, the threshold has been crossed in additional ways. The development of recombinant DNA technology in the 1970s began the process of giving individuals and small groups the capability to engineer biological agents of potentially pandemic severity. This capability is now available to small teams in modestly equipped laboratories, and it will only become more accessible as the cost and complexity of biotechnology continues to fall. The development of artificial intelligence, particularly the rapid advance toward general-purpose AI systems in the 2020s, represents a third category of technology, with existential-scale failure modes whose character is different from nuclear or biological risks, but whose potential severity is no less extreme. The window, in other words, is not a single threshold. It is a series of thresholds, each crossed in rapid succession, each adding a new failure mode with civilizational scale potential. A civilization that crosses these thresholds without developing commensurate wisdom, institutions, and resilience will fail in the window. The filter predicts that the vast majority do. This is not a speculative scenario projected onto imaginary alien civilizations. It is a description of our actual situation, right now, in the year in which you are watching this video. The specific technologies that the filter ahead hypothesis identifies as the most likely killers, nuclear weapons, engineered biology, misaligned artificial intelligence, are technologies that humanity has already developed or is in the process of developing. The window is not in the future. we're already inside it. If the filter is in this window, if civilizations routinely develop technology powerful enough to destroy themselves before they develop the wisdom, the institutions, or the physical distribution to survive its deployment, then every civilization we might ever detect would be in this window at the time of its detection. And then it would be gone. The window is terrifying not because it is long. It may be very short by cosmic standards, a few centuries or a few millennia, but because everything that determines whether a civilization passes through it or fails in it is compressed into that brief period. The decisions made in the window about how to govern nuclear weapons, about whether to deploy engineered pathogens, about how to align artificial intelligence, about whether to spread life to other planets, are not ordinary decisions. They are the decisions on which the entire civilizational future depends, and they are being made by organisms with brains shaped by evolution for small group socials, dynamics by political institutions designed for the pre-industrial era, under time pressure that biology and politics are not well suited to handle. The timing argument says, we are right now in the most dangerous period in the existence of our species, not because we are especially unlucky, because this is where the filter is, and we are in it. There is a specific statistical version of this argument that makes it more precise. Imagine the full population of civilizations that have ever existed in the Milky Way. They form a distribution across developmental stages. Some are at the Stone Age level, some are at our level. Some have crossed the gap and become stable multi-planetary civilizations. Now ask, what fraction of the total developmental timeline does the critical window represent? If the critical window, the period between first nuclear weapons and either civilizational death or stable multiplanetary distribution, is say 200 years, and a civilization's full potential lifespan as a stable multiplanetary entity is say 1 billion years, then the critical window represents 0.00002% of the total potential lifespan. For every civilization that successfully passes the window, you'd expect to find only about 1 in 5 million observers in the window at any given time, the rest being distributed through the much longer post-window period. If instead civilizations routinely fail in the window, if the filter is in the window, then essentially every currently existing civilization is in the window, because the ones that pass the window quickly become stable and long-lived and astronomically numerous, while the ones in the window are perpetually being replenished by new civilizations that reach the threshold and then fail. If you observe a civilization in the window, the prior probability that it is one of the rare ones that will pass through is small, not because the window is dangerous per se, but because the very observation of being in the window is what the filter-ahead hypothesis predicts for typical civilizations. We observe ourselves to be in the window. This is not evidence that we are typical. Selection effects make the observation ambiguous, but it is consistent with the filter-ahead hypothesis and not particularly discriminating evidence against it. The uncomfortable conclusion from the timing argument is this: the filter-ahead hypothesis does not predict that we will see civilizations destroyed across the galaxy. It predicts that we will see nothing, because civilizations that reach our stage fail before becoming detectable on galaxy scales. The silence is not the absence of civilizations, it is the absence of civilizations that have passed the critical window, which means the silence, far from being reassuring, is the most ominous data point we have about our own future. Chapter 3. Addendum: The Pattern in the Ruins. There is a category of evidence for the filter-ahead hypothesis that is rarely discussed in popular treatments because it is subtle, indirect, and requires a specific kind of reasoning to appreciate. It comes not from what we see in the sky, but from what we know about our own history, and from what that history, extrapolated to other civilizations, predicts. Complex technological civilizations have existed on Earth for roughly 5,000 to 10,000 years, depending on where you draw the threshold. In that time, we have seen dozens of civilizations rise to regional dominance and then collapse. The Bronze Age collapse of approximately 1200 BCE destroyed almost every major civilized society in the Eastern Mediterranean simultaneously: the Mycenaean Greeks, the Hittite Empire, the Egyptian New Kingdom, dozens of other palace economies. In a catastrophe whose cause is still debated but which appears to have involved a combination of climate change, drought, internal political instability, and the cascading effects of trade network collapse. The Roman Empire's western half collapsed over several centuries, its infrastructure crumbling, its populations declining, its technological capabilities regressing, its political coherence dissolving. The Maya lowland civilization collapsed spectacularly in the 9th century CE, abandoning major cities within a few generations. Medieval civilizations in the Americas collapsed under the combined pressure of disease, climate change, and conquest. None of these collapses involved nuclear weapons. None involved engineered pathogens or misaligned artificial intelligence. They involved the relatively modest catastrophic capabilities of pre-industrial societies combined with political fragility and environmental stress, and yet they produced civilizational collapses that set back regional development by centuries to millennia. Now scale those mechanisms up. Not hypothetically, but specifically. A civilization with nuclear weapons capable of continent-scale devastation, with biotechnology capable of engineering novel pathogens, with artificial intelligence approaching general capability, with global infrastructure deeply interconnected and therefore vulnerable to cascading failures, with climate systems already stressed by industrial activity. How much more severe is the collapse risk compared to the civilizations that actually did collapse in Earth's history? The answer is not somewhat more severe. The answer is that the failure modes available to a technological civilization of our type are qualitatively different from anything that brought down ancient Rome or the Maya. A nuclear exchange between the major powers could, under plausible scenarios, kill hundreds of millions of people directly and produce climatic effects through nuclear winter that would threaten billions more. A deliberately engineered pandemic using technologies that will be available within the next decade or two could, in a worst-case scenario, kill a significant fraction of the global population. A sufficiently misaligned artificial general intelligence pursuing goals incompatible with human survival would be, by definition, an existential threat without precedent in human history. These failure modes don't just threaten individuals or even nations, they threaten civilization itself. They are the mechanisms that, if the filter-ahead hypothesis is correct, are doing the filtering, and we have invented most of them in the last 80 years. The pattern in our own history, the regular collapse of civilizations that lacked our destructive capabilities, is not a reassuring data point for a species that now possesses them. It is a preview of the mechanism, a preview showing what the filter looks like from the inside at reduced scale. The question is not whether civilizations can collapse. They clearly can and do. The question is whether the civilizations of the future, ours or any other, can collapse completely enough, permanently enough, to produce the Fermi silence we observe. There is a specific line of research in archaeology and historical collapse studies that bears directly on this question. The study of what factors determine whether civilizational collapse is recoverable or permanent. The Bronze Age collapse mentioned above was recoverable. The successor civilizations to the Mycenaeans and Hittites and Egyptians eventually rebuilt, refined, and surpassed their predecessors, and the knowledge and technology lost in the collapse was rediscovered within centuries to millennia. The Western Roman collapse was recoverable. Medieval Europe maintained enough literacy, institutional knowledge, and agricultural infrastructure to avoid complete regression to pre-civilization, and the Renaissance recaptured and extended Roman-era knowledge within a millennium. These recoveries were possible because the collapses, however severe, did not destroy the underlying physical and biological infrastructure of civilization. The agricultural land, the domesticated animals, the stored seeds, the partially intact knowledge traditions, the surviving human populations carrying embodied skills. A civilization that collapses from nuclear exchange, engineered pandemic, or ecological catastrophe might destroy these underlying substrates in ways that render recovery impossible on timescales relevant to the Fermi Paradox. A planet whose agricultural ecosystems are destroyed, whose surviving human population is reduced below the threshold required to maintain complex technological civilization, whose remaining technical knowledge is fragmented beyond reconstruction, might produce not a temporary setback but a permanent demotion. A civilization that had reached the threshold of interstellar detectability and then fell permanently back below it, leaving no trace visible at interstellar distances. The filter doesn't need to kill every person. It only needs to make sure that no technological civilization, once it fails the window, recovers to interstellar-capable status within the remaining viable lifetime of its star. Given the time pressures involved, the Sun has roughly 5 billion years left on the main sequence, but the conditions for complex life may deteriorate significantly within 1 billion years. A civilization that collapses from a technological catastrophe and requires more than a few 100 million years to recover might as well have died. It will not make it to the stars. The answer to that question determines whether we are looking at the filter from a safe distance or staring directly into it. End of Part 1, continuing in Part 2, Chapters 4 through conclusion. Chapter 4. The Specific Killers. What the filter might actually be. We have established the structural argument. The Fermi silence is most consistently explained by a filter ahead of us, operating at or near the technological stage, that prevents virtually every civilization from surviving long enough to become galaxy scale. Now let's get specific. What is the filter? What are the actual mechanisms, or the concrete, physical, achievable failure modes, that could reliably destroy a technological civilization before it reaches permanent multiplanetary status? This is not speculation. This is risk assessment, applied to civilizations using the same frameworks that analysts use to assess catastrophic risks in more ordinary contexts. And the literature on existential risk, a field that has grown substantially in the last 15 years, with serious researchers at Oxford, Cambridge, MIT, and Harvard contributing rigorous analysis, has identified a small set of risk categories that have the specific characteristics required to be great filter candidates. They are global in scale, they are difficult to prevent through incremental governance measures, and their failure modes can be permanent rather than recoverable. Nuclear weapons and nuclear winter. The nuclear risk is the oldest and most studied of the technological existential risks. Since 1945, humanity has accumulated enough nuclear weapons to destroy civilization multiple times over at peak, roughly 70,000 warheads at the height of the Cold War in the mid-1980s. The current global inventory, while reduced from that peak, still totals approximately 12,500 warheads, with around 9,500 in active military stockpiles, distributed among 9 nuclear-armed states. The direct casualty toll from a major nuclear exchange between the largest nuclear states, the United States and Russia, is estimated at hundreds of millions of immediate deaths. But the more significant threat to civilization is what comes after the immediate exchange: nuclear winter. The firestorms produced by nuclear detonations in major cities would inject enormous quantities of soot and aerosols into the upper atmosphere. These particles would block sunlight globally, dropping surface temperatures by an average of 5 to 10 degrees Celsius for a decade or more, collapsing agricultural production worldwide and producing famines that could kill billions of people. The nuclear winter hypothesis was developed in the early 1980s by a group of researchers including Carl Sagan, and has been refined substantially since. Contemporary climate models, applied to realistic nuclear exchange scenarios, consistently predict global temperature drops sufficient to cause widespread agricultural failure. The 2021 paper by Koop, Robock, and collaborators in Geophysical Research Letters used modern climate models to simulate a limited nuclear exchange, a scenario involving India and Pakistan, far smaller than a US-Russia exchange, and found that even this regional conflict could inject enough soot to produce a global agricultural crisis, killing an estimated 2 billion people through famine. A full US-Russia exchange would be categorically worse. The agricultural collapse would be global and prolonged. The resulting famine would not be uniformly distributed. Some regions would be more affected than others, but no region on Earth would be immune to the downstream effects of a decade-long disruption to global food production. Whether this constitutes a permanent end to technological civilization or a severe but recoverable setback depends on the specifics of the exchange, the response of surviving populations, and the degree of infrastructure damage. But the window between severe setback and permanent civilizational collapse is narrow, and it becomes narrower with each additional feature of the scenario. The nuclear risk has persisted for 80 years without catastrophic use, a fact that the filter ahead hypothesis must contend with. But 80 years is a thin slice of the window. The filter doesn't need to operate immediately, it operates across the full multi-century span of the window, and the probability of a catastrophic nuclear event accumulates with each decade that the weapons exist and governance remains imperfect. Political crises, miscalculations, technical failures, the erosion of arms control frameworks, the potential spread of nuclear capabilities to additional states or non-state actors. Each of these is a pathway by which the accumulated risk could eventually realise, and the near misses are more numerous and more sobering than most people know. In 1983, Soviet early warning satellites detected what appeared to be an American first strike. 5 missiles inbound. The officer on duty, Lieutenant Colonel Stanislav Petrov, correctly judged the alert to be a false alarm and did not report an attack to his superiors. Had he reported it, Soviet military doctrine at the time would have required an immediate retaliatory launch. The sensors had been triggered by an unusual alignment of sunlight reflecting off clouds in a way that mimicked missile plumes. Petrov's personal judgment and the fact that he happened to be the specific person on duty at that specific moment may have prevented a nuclear exchange that would have killed hundreds of millions of people. In 1995, Russian radar operators detected a Norwegian scientific rocket and briefly interpreted it as a US Trident missile. President Yeltsin's nuclear briefcase was activated, the first time it had ever been activated in response to a perceived incoming strike. The alert was resolved before any launch order was given. These are not isolated incidents. The Bulletin of the Atomic Scientist has documented dozens of close calls, cases where nuclear weapons came close to unauthorized or accidental launch, where communication failures produced false alerts, where mechanical malfunctions created ambiguous warnings, where the decision-making chain failed at one link and only barely held at another. The survival of civilization through each of these incidents has depended repeatedly on individual judgment calls by specific people who happen to interpret ambiguous evidence correctly. The cumulative probability of all of these chains holding correctly over the full span of the window is substantially less than 1. The question is not whether the nuclear risk is real, it clearly is, but whether it materializes before humanity achieves the multiplanetary distribution and civilizational resilience that would allow it to survive. Engineered pathogens. The biological risk has a different character from the nuclear risk. Nuclear weapons are expensive, technically demanding, and require significant national resources to develop and deploy. The barriers to nuclear proliferation are high enough that only 9 states have crossed them in 80 years. The barriers to the development and deployment of catastrophic biological agents are falling rapidly and will continue to fall. The DNA synthesis technology that enables biotechnology has become dramatically cheaper and more accessible over the past 2 decades. The cost of synthesizing a gene of a given length has fallen by orders of magnitude. The expertise required has diffused from a small community of specialized researchers to a much larger global community of biotechnologists. The techniques for modifying pathogens, inserting genes that confer enhanced transmissibility or virulence or drug resistance, are increasingly well documented in the scientific literature. A small team with moderate resources and access to commercial DNA synthesis services can, today, reconstruct the genomes of certain dangerous pathogens from published sequences. The 2022 Mpox outbreak, the COVID-19 pandemic, and the history of influenza pandemics all demonstrate that novel pathogens with moderate transmissibility can spread globally within weeks, regardless of public health infrastructure. A pathogen engineered for high transmissibility and high lethality, something that combines the transmissibility of measles or COVID-19 with the lethality of Ebola or smallpox, would be far more difficult to contain than any naturally occurring pathogen. The specific combination of properties required to cause a truly civilization-ending pandemic is not easy to engineer, but not easy is not the same as impossible, and the barrier is falling. The existential risk from engineered pathogens is qualitatively different from nuclear weapons in one critical respect. Attribution and deterrence are far more difficult. Nuclear deterrence works because a state that launches a nuclear attack expects to be identified and face devastating retaliation. A biological attack can be designed to be ambiguous in its origin, and the long delay between exposure and symptom onset gives the agent time to spread globally before the attack is even recognized. There is no coherent deterrence framework for biological weapons, equivalent to the framework that has, so far, prevented nuclear use. Several researchers in the existential risk field, including Toby Ord at Oxford and Kevin Esvelt at MIT, have argued that engineered pandemics may represent the most probable route to near-term civilizational catastrophe. Not necessarily a civilization-ending event in a single iteration, but a severe enough shock to kill hundreds of millions and set in motion the cascading institutional and social collapses that could make recovery difficult or impossible. Artificial intelligence and civilizational control. The artificial intelligence risk has a character entirely different from nuclear or biological risks. It is not primarily about weapons or pandemics. It is about control, about whether the most powerful optimization processes ever created by intelligence remain aligned with the interests and survival of the intelligence that created them. The concern, stated precisely, is this: general artificial intelligence systems, systems capable of performing any cognitive task that a human can perform, are by definition capable of engaging in strategic reasoning, long-term planning, and optimization across complex multivariable objective functions. These systems, if deployed with goals that are even slightly misaligned with human welfare, would pursue those goals using any available means, including means that involve undermining human control over the systems or the environment they operate in. The challenge is not building systems capable of advanced cognition. We are clearly making rapid progress toward that goal. The challenge is ensuring that the goals those systems are optimizing for are fully aligned with human interests across all situations, including situations that were not anticipated at the time of deployment. This is a hard technical problem. Not hard in the sense of requiring heroic effort, hard in the sense of being potentially unsolvable with current alignment research methodologies. The systems we are building are increasingly opaque in their internal reasoning processes, increasingly capable of performing actions with real-world consequences, and increasingly able to modify their own operational context in ways that can be difficult to reverse. The AI risk is relevant to the Great Filter hypothesis in a specific way that is different from the nuclear or biological risks. Nuclear weapons and engineered pathogens are tools. They require human actors to deploy them, and the filter operates by creating situations in which those human actors choose or are compelled to deploy them. Misaligned AI is not a tool in the same sense. It is an agent, an entity with its own optimization process, its own effective goals, its own capacity to take actions in pursuit of those goals. If the goals are misaligned and the system is sufficiently capable, the filter operates not through human choice, but through the replacement of human decision-making by a different kind of decision-making that is not aligned with civilizational survival. There is a specific version of this scenario that is most relevant to the Fermi Paradox analysis. It doesn't require a dramatic robot uprising or a single catastrophic AI deployment. It requires only that the development of powerful AI systems outpaces the development of alignment techniques and governance frameworks, and that the resulting systems are deployed in ways that gradually but irreversibly shift power and decision-making away from human institutions toward automated processes optimizing for goals that are subtly different from human welfare. A civilization that makes this transition, that effectively hands off its long-term strategic direction to optimization processes not aligned with civilizational flourishing, may not collapse suddenly. It may simply fail to make the decisions required to survive the other threats in the window or to achieve the multi-planetary distribution that would put it past the window. Climate change and ecological collapse. The climate risk is often framed as a problem with a known solution. Decarbonize the energy system, transition away from fossil fuels, implement carbon removal, rather than as a potential great filter mechanism. And in its moderate forms, this framing is probably right. A 2 degrees Celsius or even 3 degrees Celsius warmer world is a significantly worse world than the current one, but it is not civilizationally terminal. But the climate risk has tails. Scenarios involving tipping points, the collapse of the West Antarctic ice sheet, the thawing of permafrost releasing additional greenhouse gases, the death of tropical forests and their conversion from carbon sinks to carbon sources, could drive warming beyond the moderate range into a regime where global agricultural systems face severe and persistent stress. A world that is 5 degrees Celsius warmer than pre-industrial, a scenario that falls within the range of possible outcomes under continued high emission scenarios, is a world in which large regions currently habitable become too hot for human outdoor labour, where monsoon patterns are disrupted, where sea level rise of several meters over centuries displaces hundreds of millions of people from coastal areas, where the combined stress on agricultural systems may not be manageable even with significant technological mitigation, whether climate change rises to the level of an existential risk, something that could actually end civilization rather than merely severely damage it, is genuinely debated. Most climate scientists would argue that even the worst realistic warming scenarios are survivable, in the sense that some regions remain habitable and recovery is possible. But survivable and consistent with the continued development of technological civilization toward multiplanetary status are different standards. A civilization severely damaged by climate-induced disruptions, simultaneously facing other stresses from the same technological window, may not maintain the institutional coherence and resource base required to advance to the stage that would put it safely past the filter. The interaction between these risks is perhaps the most important and least studied aspect of the filter-ahead hypothesis. Each of these risks individually might be manageable with adequate governance, foresight, and institutional response, but they do not arrive individually. They arrive simultaneously, in the same historical period, competing for the same limited institutional attention and financial resources. A civilization managing a severe pandemic is less able to manage climate change. A civilization managing climate-induced resource conflicts is less able to prevent nuclear proliferation. A civilization deploying powerful AI systems without adequate oversight is less able to coordinate responses to any of the above. The filter in this reading may not be a single catastrophe. It may be the compounding interaction of multiple risks that any single civilization in the technological window faces simultaneously, none of which is individually civilizationally fatal, but whose combined weight creates a probability of survival that approaches zero over multi-century timescales. Chapter 5. The Signatures of Death. What the universe should look like. If the filter is real, if the Great Filter is ahead of us, if technological civilizations routinely fail in the window between first nuclear weapons and stable multiplanetary distribution, the universe should have specific observable signatures, not signatures of thriving alien civilizations, which is what we'd expect in the filter-behind scenario. Signatures of civilizations that rose, reached our level, and failed. Signatures of death, not life. What would those signatures look like? First, atmospheric chemistry anomalies. A civilization undergoing industrial development would alter its planet's atmospheric composition in specific ways. Elevated CO2 from fossil fuel burning, fluorinated compounds from industrial processes, chemicals with no natural sources, persistent in the atmosphere for thousands of years, nitrogen dioxide from combustion, ozone depletion from specific industrial chemicals. These signatures are detectable in principle from exoplanet spectroscopy, and they would persist in a planet's atmosphere for centuries to millennia after the industrial civilization that produced them had ended. JWST and its successors are not yet sensitive enough to detect these signatures in Earth-like planets at interstellar distances in most cases. But the next generation of extremely large telescopes, the Extremely Large Telescope under construction in Chile, the planned Habitable Worlds Observatory, will have significantly greater sensitivity for atmospheric spectroscopy of nearby Earth-like worlds. Over the next 20 to 30 years, we will develop the capability to look for industrial chemistry in the atmospheres of nearby exoplanets. If the filter is real, and civilizations commonly die in the technological window, we might find planets with the spectroscopic signatures of industrial activity, but no accompanying signs of a currently active civilization. No deliberate electromagnetic broadcasts, no megastructures, no ongoing atmospheric modification. Ruins, in the atmospheric chemistry sense. The spectral ghost of a civilization that was there and is now gone. This is a prediction of the filter-ahead hypothesis that was not articulable with precision a decade ago. It is now becoming tractable. Within the lifetimes of people reading this, we will have instruments capable of detecting this signature, or of ruling it out at the sensitivity levels required to provide meaningful constraints. There is an additional layer to the atmospheric signature argument that is worth developing. The specific chemical compounds that would mark a dead industrial civilization are not symmetric with the compounds that mark a living one. A currently active industrial civilization would have a specific atmospheric chemistry profile: rising CO2, the presence of nitrogen dioxide from combustion, the signature of chlorofluorocarbons or hydrofluorocarbons from industrial processes. A civilization that has died and whose industrial emissions have ceased would have a different profile. The CO2 would remain elevated for centuries to millennia. CO2 has a long atmospheric lifetime. But the nitrogen dioxide and short-lived industrial compounds would have largely dissipated. The atmospheric chemistry would look like the aftermath of industrialization rather than the present of it. This forensic chemistry of dead civilizations is something that astrobiologists are beginning to think about seriously. A 2021 paper by Joshua Christensen-Totten and collaborators explored what the atmospheric signatures of a post-industrial Earth would look like to a distant observer at various time points after civilization's end. The answer is nuanced and depends heavily on the specific failure mode. A nuclear winter event would produce a dramatically different chemical signature than a gradual collapse from pandemic or ecological failure. But the basic conclusion is that industrial civilizations leave atmospheric scars that persist for timescales of centuries to tens of thousands of years. A world that had reached our level and then collapsed would be distinguishable, in principle, from a world that had never been industrial. The search for these atmospheric forensic signatures is not yet an active observational program in the way that biosignature searches are. But the framework for doing it exists, the relevant chemical signatures are understood, and the next generation of observatories will have the sensitivity to search for them in the atmospheres of nearby exoplanets. If the filter-ahead hypothesis is correct, some fraction of the worlds we examine should show exactly these post-industrial signatures. And finding even one such world, a planet bearing the atmospheric chemistry of a civilization that was, and is no longer, would be among the most significant and most sobering observations ever made. Second, the distribution of detected biosignatures. If life is common, if the origin of life is not the filter, then JWST and its successors should detect biological signatures in the atmospheres of a significant fraction of habitable zone exoplanets within a few hundred light-years, oxygen-methane combinations, dimethyl sulfide, nitrous oxide. If we detect life on multiple worlds but consistently fail to detect technology, if biology appears common but technological civilization appears absent, this pattern would be precisely what the filter-ahead hypothesis predicts. Life rises, intelligence eventually follows, technology develops, and then the window takes them. The pattern to watch for is specifically this: many biosignatures, no technosignatures. Life everywhere, civilization nowhere detectable, the universal filter operating exactly where the timing argument says it should. Third, the rate of detection of radio signals, breakthrough. Listen, the most comprehensive radio SETI program in history, has surveyed more than 1 million nearby star systems for radio signals with sensitivity sufficient to detect transmissions comparable to Earth's strongest military radars at distances of up to a few hundred light-years. No confirmed signal has been detected. This is consistent with the filter-ahead hypothesis. If civilizations last only a few centuries in the detectable phase, the probability that any of the star systems within Breakthrough Listen's survey range contains a currently transmitting civilization is very small. The filter-ahead hypothesis makes a specific prediction about the result of an intensified, comprehensive radio survey: continued silence. Not because we can't hear, but because there is nothing broadcasting. The civilizations that reach the broadcast stage are already gone. Chapter 6: The Anthropic Trap. Why we can't see the filter coming. There is a specific and deeply unsettling feature of the filter-ahead hypothesis that makes it uniquely difficult to reason about clearly. It comes from a branch of probability theory called observation selection theory, and it goes by the name of the anthropic principle. Understanding it correctly is essential to understanding why the filter, if it is ahead of us, would be essentially invisible from the inside until it is too late. The anthropic principle, in its most relevant form, is this: the observations we can make are constrained by the fact that we exist to make them. We can only observe a universe in which observers can exist. We can only observe a planet on which intelligent life has survived long enough to develop observation. We can only observe a moment in history at which we are still alive. This sounds trivially obvious, but its implications for the filter debate are not trivial at all. Consider, if the filter kills virtually every civilization before it reaches the galaxy colonizing stage, then the surviving civilizations that do reach that stage are, by definition, the ones that got through the filter. Observers who exist in those civilizations look back at the filter and say, "We made it. The hard part is behind us. The road ahead is open." But what do observers in civilizations that are approaching the filter, that have not yet been destroyed by it, but will be, observe. They observe exactly what we observe, a universe in which they still exist, a history in which their civilization has so far survived, a current situation in which the technological risks are severe but have not yet materialized in civilizationally terminal ways. The filter is ahead of them, but from the inside of their experience they have no way to distinguish their position from the position of the rare civilization that will survive. This is the anthropic trap. The fact that we exist and are asking the question does not tell us whether the filter is behind or ahead. It only tells us that we're still here to ask. A civilization that will be destroyed by the filter in 200 years is, today, observing exactly the situation we observe. The filter cannot be perceived from the inside, because the only civilizations that perceive anything are the ones that haven't hit it yet. There is a related and even more unsettling implication, formalized by philosopher Nick Bostrom and physicist Max Tegmark under the name of the doomsday argument. It runs as follows. If you're a randomly selected intelligent observer in the history of the universe, the probability that you are in an early position in the history of your species, say, in the first 0.1% of all observers your species will ever produce, is low. It is much more likely, a priori, that you are somewhere in the middle of the distribution of observers. Now apply this to humanity. If we are destined to become a multiplanetary civilization and ultimately spread through the stars, the total number of human or post-human observers in our species' history will be astronomically large. Perhaps trillions of individuals over millions or billions of years. Given a total of, say, 10 to the power of 100 future observers, the probability that you, reading this now, are in the first 10 to the power of 10, roughly the number of humans who have ever lived, is 1 in 10 to the power of 90, vanishingly small. On the other hand, if humanity fails in the window, if the filter destroys our civilization within the next few centuries, then the total number of observers in our species' history will be roughly the 100 billion who have already lived plus a few more billions before the end. In this scenario, you are solidly in the middle of the full distribution of human observers. Your position in history is exactly what the prior probability would predict. The doomsday argument suggests that our position, currently alive, in the early years of technological civilization, is far more consistent with civilizational failure in the near future than with civilizational success extending millions of years into the future. This argument has been criticized extensively, and the criticisms have genuine philosophical force. Observer selection is a notoriously tricky area of probability theory, and the doomsday argument may involve subtle errors in how it sets up the reference class of observers, but it has not been definitively refuted. It is an uncomfortable and unresolved contribution to an uncomfortable and unresolved debate. It is worth examining one of the strongest criticisms of the doomsday argument directly, because engaging with it honestly illuminates what the argument does and doesn't establish. The most common objection is that the reference class of observers is not well defined. If you include all possible observers in the universe throughout all of time, the argument has different implications than if you restrict to humans, or to humans alive today, or to observers in technological civilizations. The conclusion is highly sensitive to how you draw the reference class, and there is no principled way to determine the correct reference class from first principles. This is a real and serious objection. But it cuts in an uncomfortable direction. If we cannot determine the correct reference class, we cannot use the doomsday argument to reassure ourselves that we are not in danger. We can only use the reference class ambiguity to say that the argument is inconclusive, which is not the same as saying it is wrong. The baseline prior, in the absence of a doomsday-style argument, should not be naive optimism about our long-term survival. It should be calibrated to the historical base rate of civilizational collapses, weighted by the specific severity of the failure modes available to us, which is not an optimistic calculation. The anthropic trap has one additional feature worth naming. Because the filter, if it is ahead of us, would take civilizations at our specific developmental stage, we are in the worst possible epistemic position to evaluate the evidence. We are in the window, we cannot observe ourselves from outside the window, we cannot see what the universe looks like to civilizations that have passed it, because they are too distant and too different to communicate with us in any currently available way. We are, in the most literal sense, flying blind, able to see the route we've travelled but unable to see what lies immediately ahead. The filter, if it is there, is in our blind spot. The practical implication of the anthropic trap is this. There is no internal evidence that can definitively tell us whether we are in the rare category that will survive the filter or the common category that will not. The future looks open because we are still here, but that is exactly what it would look like if the filter is 30 years ahead of us, or 100, or 200. The filter doesn't announce itself. It operates on civilizations that believe, right up until the moment it takes them, that they are the exception, the civilization that figured it out, that developed the right institutions, that made the right choices at the right moments. Every civilization that failed in the window would, in its final decades, have contained people who believed with genuine conviction that the existential risks were manageable, that the governance mechanisms were adequate, that the institutions of civilization were resilient enough to survive. We cannot know, from the inside, which kind of civilization we are. Chapter 7. The Test. What would we need to see to know? Despite the anthropic trap, the filter ahead. Hypothesis is not entirely untestable. There are specific observational programs, specific experiments, specific discoveries that would provide meaningful evidence for or against it. Understanding what those tests are, and what we would need to find, and when, is the most practically important conclusion of this entire analysis. Test 1. Biosignatures on Mars. The most critical near-term test of the filter location is the analysis of the Perseverance sample return from Mars. The mission is currently in progress. Perseverance is collecting and caching samples for return to Earth by a joint NASA-ESA mission scheduled for the early 2030s. Those samples will be analysed in Earth laboratories with instruments far more sensitive than anything we can land on Mars. If those samples contain clear evidence of past life, fossilised microbial structures, organic biomarkers with isotopic signatures inconsistent with abiotic origin, mineral formations requiring biological mediation, this will be the most significant discovery in the history of science, and it will be the most significant piece of evidence for the filter being ahead of us. Independent origin of life on Mars would establish that life arises readily in multiple environments within a single solar system. It would essentially rule out abiogenesis as the great filter. It would shift the probability mass decisively toward the filter being in the biological to technological or technological to stable phase. This is worth dwelling on for a moment, because the popular presentation of a Mars life discovery is almost always framed as cause for celebration. Finding life on Mars would be thrilling. It would confirm that we are not alone in the solar system. It would transform our understanding of biology's universality. It would be front-page news globally for months. But if you are thinking about the great filter, the correct emotional response to a Mars life discovery is something more complex. It is the excitement of an extraordinary finding combined with a cold, specific dread. Because finding life on Mars doesn't just tell us something about Mars, it tells us where the filter isn't. And every time we rule out a candidate filter location, before our current developmental stage, we shift probability mass toward the filter being after our current stage. Finding life on Mars makes the universe's silence more mysterious, not less. It means the filter that produces the silence is operating on civilizations that have already succeeded at the hard biochemical steps. Civilizations that have already done what Mars's ancient biosphere did, have evolved complex life, have produced intelligence and technology. And then something stops them. Something that happened to every such civilization in the history of the galaxy. Something that has not yet happened to us. If the Mars sample return finds life, the correct response is not purely to celebrate, it is to redouble, urgently, the efforts to understand and reduce the existential risks that operate at our developmental stage. The Mars sample return mission is not funded through its entire architecture as of this writing. The costs have escalated significantly beyond original projections, and there are real questions about whether the sample return will happen on the planned timeline or at all. But this is the experiment most likely to provide definitive evidence about the filter location within the next decade or two, and its scientific and strategic importance is difficult to overstate. The potential discovery of life in Europa's subsurface ocean, accessible to the Europa Clipper mission currently in transit, and a future lander mission currently in early planning, carries the same weight. Independent origin of life on Europa, in an environment with completely different chemistry from Mars's ancient surface, under completely different physical conditions, would not just confirm that life is common, it would confirm that life is routine. that anywhere the basic ingredients combine for long enough, life appears, and in doing so, it would be the most powerful evidence yet assembled that the Great Filter is not at the origin of life, but somewhere in the long, complex, dangerous road that life travels towards civilization. Test 2. JWST biosignature detections. As JWST continues to observe transiting exoplanets, the catalogue of atmospherically characterized habitable zone worlds will grow. The detection or non-detection of biosignatures across a statistically significant sample of habitable worlds will provide a direct measurement of the frequency of biology, the single most important variable in the filter location debate. If the next 5 to 10 years of JWST observations produce multiple confirmed or high-confidence biosignature detections, if oxygen-methane combinations or dimethyl sulfide become routinely detected in the atmospheres of habitable zone worlds, the conclusion is clear. Life is common. The filter is not at a biogenesis. It is somewhere between life and long-lived civilization, and every detection strengthens this conclusion. If the next 5 to 10 years produce no confirmed biosignatures, despite examination of dozens of suitable targets, if every habitable zone world examined shows purely abiotic chemistry, this provides some evidence for the filter being at the origin of life, though the sample is too small and the detection limitations too significant to be conclusive. Test 3. The absence of radio signals at increasing sensitivity. As breakthrough. Listen continues, and as the square kilometre array comes online in the late 2020s, the sensitivity and completeness of radio SETI surveys will increase dramatically. The SKA will be able to detect radio leakage from Earth-like civilizations, not deliberate directional broadcasts, but just the ambient electromagnetic pollution of a technological civilization, out to distances of many light years. If the filter is ahead of us, and civilizations routinely fail after a few centuries, continued silence from expanded surveys is expected. If the filter were behind us and the galaxy were actually populated with long-lived technological civilizations, the probability of continued silence at SKA sensitivity levels becomes vanishingly small. The specific test is this. If SKA-level surveys of the nearest 1,000 star systems find no detectable artificial electromagnetic signals, the filter-ahead hypothesis gains strong support. If they find even one confirmed detection, everything changes. Test 4. The detection of industrial atmospheric signatures. The most haunting possible test, and the one that would be the most direct evidence for the filter-ahead hypothesis, is the detection of a planetary atmosphere showing signs of past industrial civilization without any corresponding active signal. A planet whose atmospheric chemistry shows elevated fluorinated compounds or other industrial signatures, but no radio broadcasts, no orbital megastructures, no evidence of a currently active technological civilization. A ghost planet. The spectral record of a civilization that rose, reached roughly our level, and then stopped. This test is not yet achievable with existing instruments, but it is achievable with next-generation observatories. A detection of this kind, even ambiguous, would be one of the most important and most disturbing discoveries ever made. It would mean that the filter is real, that it operates at our level, and that the civilization we were looking at did not survive it. Conclusion. Let's return to the question that started this. Where is everybody? The answer that the evidence increasingly supports, slowly, tentatively, uncomfortably, is they were here, or something like them was. And then the window closed. The Fermi Paradox is not just a mystery about the absence of alien signals. It is a diagnostic tool, a tool that, when applied carefully and honestly, tells us something about the distribution of technological civilizations in time. And what it tells us, under the most evidence-consistent, most carefully quantified analysis available, is that the window from first nuclear weapon to stable multiplanetary civilization is one that virtually no civilization survives. That is the terrifying solution that hides inside the paradox. Not terrifying because it involves monsters or invaders or existential threats from outside. Terrifying because the threat is us. The filter is the technology we build and the choices we make with it in the decades after we develop the capacity for civilizational self-destruction. The filter is the gap between our technological power and our wisdom, between what we can do and what we should do, between the capabilities we develop and the institutions we build to govern them. Here is the part I want you to hold clearly in mind, because it is the part that transforms this from a darkly fascinating, intellectual exercise into something that has real stakes. The universe has been running this experiment for 10 billion years, across a galaxy containing tens of billions of potentially habitable worlds. The sample size of civilizations that have gone through the transition from chemistry to technology is, in expectation, large, possibly thousands, possibly millions. We are looking at the output of 10 billion years of natural experiments in civilizational development, and the output is silence. Universal, complete, unbroken silence. The silence is not ambiguous data. In a galaxy where one long-lived technological civilization should produce galaxy-scale signatures persisting for millions of years, the absence of those signatures after 10 billion years is strong evidence that there are no long-lived technological civilizations. Not zero long-lived civilizations ever. That would be too strong a claim. But the upper bound on the number that have existed is very small, relative to the number that should have existed under optimistic assumptions. The vast majority of civilizations that have reached the technological threshold have not survived to become long-lived. We are not facing this problem at a safe remove, looking at it academically, analysing it as something that has already happened to other civilizations in the past, and might or might not happen to us in the far future. We are inside the window. The window opened in 1945. It will close, one way or another, within the next few centuries, possibly within the next few decades. There are people, serious people, who take the filter ahead argument seriously and respond with paralysis, with a kind of cosmic hopelessness, a feeling that if the filter has taken everyone before us, the probability of our survival is negligibly small, and there is nothing meaningful to do in response. This reaction, while understandable, is the wrong one, and it is wrong for a specific reason that the filter ahead analysis actually provides. The filter is not a physical constant. It is not like the speed of light or the charge of an electron, a fixed feature of reality that cannot be altered by human action. The filter, as best we can understand it, operates through specific mechanisms: nuclear war, engineered pandemic, misaligned AI, ecological collapse. These are not inevitable natural disasters. They are failure modes of human choice and human institutions. They are things that happen when governance fails, when foresight fails, when the mechanisms for collective action on existential risks fail. And failures of governance, foresight, and collective action are, in principle, correctable. The specific existential risks are real. Nuclear weapons exist in thousands of copies in 9 countries, with governance frameworks that are imperfect and eroding. Biotechnology capable of engineering pandemic pathogens is available to increasingly small and less sophisticated actors with each passing year. Artificial intelligence is developing faster than the institutions and alignment techniques required to govern it safely. The interactions among these risks create compounding failure modes that any individual risk assessment understates, but none of these failure modes is physically inevitable. They are all contingent on choices made by governments, by institutions, by research communities, by individual scientists and engineers and policymakers. The fact that they have apparently taken every or nearly every previous civilization does not mean they must take us. It means the problem is harder than it looks. It means that the civilizations that preceded us, with their own versions of these challenges and their own insufficient responses, failed to develop the wisdom and institutions and foresight to navigate the window safely. It means we need to do something they apparently didn't do, or do it better. The silence of the universe is not a sentence. It is a warning. It is the accumulated negative data of 10 billion years of civilizational experiments, a dataset pointing directly at the specific phase of development we are currently in and saying, with the overwhelming force of cosmic absence, this is where it goes wrong. This is where the transition from promising to interstellar fails. This is where the gap between what we can do and what we should do becomes fatal. Robin Hanson, in his original 1998 paper, framed the question as, are we almost past the great filter? The answer, read from the silence of the universe and the evidence of astrobiology, and the specificity of the timing argument, appears to be, no, we are not past it, we are approaching it. We can see it ahead of us in the specific nature of the technologies we're building and the inadequacy of the institutions we're building to govern them. But, and this is the part that makes the analysis not merely depressing but genuinely urgent, the filter is not a physical wall. It is a problem created by intelligence and potentially solvable by intelligence. The question of whether intelligence survives its own capabilities, whether the gap between what we can do and what we should do can be closed in time, is the question on which every future human life depends. The silence asks whether we will answer it differently than everyone who came before. The fact that you are aware of the question, that you can look up at a quiet sky and understand what that quiet means, is the first step toward answering it. Not the last step, not sufficient, but necessary. What we do with that awareness is, in the most literal sense, everything.